All right, today we're going to talk about one of my favorite things to let students know about in tutoring, and that is Pascal's triangle. Pascal's triangle is related to the binomial theorem. It's also related to the idea of combinations that we talked about at the end of our last video. So if you want to go back and see that, that would maybe be helpful here to understand another way that we get to use this besides binomial expansion. So let's go ahead and talk about today's co-requisite skills. So let's first use Pascal's triangle to expand a binomial. So Pascal's triangle helps us find the coefficients of the terms in the expansion of a binomial. To find the coefficients of the terms, we write our expansion focusing on the coefficients. We rewrite the coefficients to the right. This is the red numbers here, forming an array of coefficients. This is the triangle over here. The array is called Pascal's triangle. So let's talk about how to form this triangle without actually doing the expansion, because the point is to go from the triangle back to the binomial expansion. Notice that in each expansion, the powers of A in each term decrease from n to 0. So they're using A and B here, and they're going from, let's say here on the 5th degree polynomial, it's A to the 5th, then A to the 4th, and A to the 3rd, A squared, A, and then finally there's 0 A's, right? And the powers of B increase from 0, that there's 0 B's here, all the way to B to the 5th. And together, the A's and B's have to always add together the powers of them to give you this degree here. So the degree of each term is always going to be degree 5 in this 5th degree binomial expansion. Here, all 5 are A's and there's 0 B's. Here, there's 4 A's and 1 B. Here, there's 3 A's and 2 B's. Here, there's 2 A's and 3 B's. Here there's 1 A and 4 B's, and here there's 0 A's and 5 B's. So now that you understand how the powers work, let's talk about getting these coefficients that are in red here. Notice each number in the array is the sum of the two closest numbers in the row above. So it's going to form this triangle. If you can add 2 numbers above and put another number in the middle, that's what you do. You bring ones along the outside, then 1 plus 1 gives me 2, 1 plus 2 gives me 3, 2 plus 1 gives me 3, 1 plus 3 gives me 4, 3 plus 3 gives me 6, 3 plus 1 gives me 4, and so on. 1 plus 4 is 5, 4 plus 6 is 10, 6 plus 4 is 10, 4 plus 1 is 5. Notice that the triangle is symmetric along this line right here. So if I know this is 1, 5, 10, and I hit this line in the middle, then it has to repeat 10, 5, 1. So you really only need to find the first half, and then it's going to be the mirror image on the other side. So again, they want you to find the next row. So after 1, 5, 10, 10, 5, 1, which is n to the 5th. So they want you to find the coefficients for n to the 6th, with n being 6. And so you can bring the ones down. 1 plus 5 is 6. 5 plus 10 is 15. 10 plus 10 is 20. 10 plus 5 is 15. 5 plus 1 is 6, and so on. So since we have those numbers in blue there, we should be able to read those as the coefficients. We should be able to write this now as 1x to the 6th plus 6x to the 5th, y to the 1st plus 15x to the 4th, y to the 2nd plus 20x to the 3rd, y to the 3rd, plus 15x to the 2nd, y to the 4th, plus 6xy to the 5th plus 1y to the 6th. And you know that we don't normally write coefficients of 1. So I'm going to get rid of those. And we did not have to sit here and write x plus y times 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 x plus y. 1, 2, 3, 4, 5, 6, and we did not have to use our distribution technique there, where we would be prone to make probably some arithmetic mistakes if we had to do it that way. This just gets us the answer in pretty much one step. So a much more efficient tool, as long as the n is not too large here and we don't have too many rows of Pascal's triangle. Even if n was larger though, Pascal's triangle would still be more efficient than doing it by hand. So there you go. That's the answer that we came to. In these examples so far, both of these things were positive. I might do an example with you in a little bit where there's a minus sign in between. See how that changes things if they don't give an example of that. So let's go ahead, and we're on row 5 now. 0, 1, 2, 3, 4, 5. Notice I started counting at 0, so they've highlighted which row that is, that it's this row that's in red. And now we've got a number there, 3, instead of just a y or a b or something like that. So I'm actually going to have to put in 3 to the 1st and 3 to the 2nd, all the way up to 3 to the 5th. So when I do that, this is going to be 1x to the 5th plus 5 times x to the 4th times 3 to the 1st times 10x to the 3rd times 3 squared times 10 or plus 10 times x squared times 3 to the 3rd plus 5 times x to the 2nd times 3 to the 4th plus 1 times 3 to the 5th. And I appreciate that they've gone ahead and raised 3 to the power of on all of these here. So 3 to the 1st is 3, 3 to the 2nd is 9, 3 to the 3rd is 27, 3 to the 4th is 81, 3 to the 5th is 243. Now we're going to have to take this 3 times this 5 to get this coefficient of 15 here on x to the 4th. This 9 times this 10 gives us 90. This 27 times this 10 gives us 270. This 81 times this 5 gives us 405. And 1 times 243 is 243. All right, we do have a minus sign here, and they made it harder because they put 3x and -2. So we're going to have, notice, let's go ahead and draw our triangle here. Row 0, row 1, row 2, row 3, row 4. Like that. So there's our coefficients right there for row 4. And so we're going to have 3x raised to the 4th, -2 raised to the 0, plus 4 times 3x raised to the 3rd, -2 raised to the 1st, plus 6 times 3x raised to the 2nd, -2 raised to the 2nd, plus 4 times 3x raised to the 1st, -2 raised to the 3rd, plus 1 times 3x raised to the 0, -2 raised to the 4th. So you see that there's going to be some sign changes here based off of if there's an even or odd power on the negative part. So 3 to the 4th, we just saw was 81, x to the 4th times 1 plus 4 times 27 x to the 3rd times -2 plus 6 times 9x squared times +4 plus 4 times 3x times a -8 plus, that's going to be 16 over there. This is going to be 81x to the 4th. This is going to be 108 to 16 x to the 3rd. Then this is going to be 36 times 6. It's going to be 216 x to the 2nd. This is going to be negative, and then that's 32 times 3 is 96. And there we go. Much, much easier than doing it the old way, right? So they're going to go ahead and walk us through that. 81, -216, +216, -96, and +16. So we got it right, okay? Went through the right process. Now we're going to use Pascal's triangle to expand a plus b to the 4th. So that's going to be a to the 4th plus, and we're using these red numbers right here, plus 4a to the 3rd b plus 6a squared b squared plus 4ab to the 3rd plus b to the 4th. Use Pascal's triangle to expand y plus 3 to the 5th. So that's going to be y to the 5th plus, then we're right here on this row. So that's 5 times 3 is 15, y to the 4th plus 3 squared times 10 is going to give me 90, y to the 3rd, plus 27 times 10 is going to be 270, y squared, plus 81 times 5 is 405y, plus 81 times 3 is 243. There we go. Use Pascal's triangle to expand 2x minus 5 raised to the 3rd. So we're on this row of 1, 3, 3, 1. And so this is going to be 2x to the 3rd is going to be 8x cubed. Then this is going to be plus, I'm just going to write this, 2x squared -5 plus 2x times -5 squared. This is 3. One of these is 5. Okay. Be consistent here. 8x to the 3rd. 4 times 3 is 12, times the -5 is -60. 25, 50, 150. That's minus 125. So now let's talk about another application of this, which I talked about a little bit last time. But let's say that I wanted 5 choose 3. I think we talked maybe not about this specific example, but if I had 5 people and I wanted to choose a committee of 3 people to represent them, and I showed you the formula method about how NCR is n factorial over r factorial times n minus r factorial, and I explained to you what factorials were, and it was big and it was messy. Well, now let's come to row 5 and let's count to column 3, starting with zeros. So 0, 1, 2, 3, 4, 5. There's n equals 5. And then r is 0, 1, 2, 3. And my answer to this problem is 10. Let's prove it to you, though, with the old formula method so you can see that this is going to work. And this is a much superior way to evaluating combinations like this. So 5 factorial over 3 factorial times 5 minus 3 factorial is 5 times 4 times 3 factorial over 3 factorial times 2 factorial. Those will cancel. 5 times 4 is 20. 2 factorial is 2. 2 goes into 20 10 times, and the answer was 10. You can just imagine how much better this is if you don't have a calculator. One other idea that I said that I wanted to introduce you to that the triangle here doesn't necessarily help you with, though, that is different from combinations, is something called permutations. So combinations were when everyone was equal and order didn't matter. Let's say that I have 5 people again, and I want to choose 3 people, but they're all for different positions on the board or something, and it's like, say, president, vice president, and treasurer or something like that. So 5P3, where order does matter, and there is no Pascal's triangle method for this. This is just going to be n factorial over n minus r factorial. It's going to be 5 factorial over 5 minus 3 factorial. It's going to be 5 factorial over 2 factorial is 5 times 4 times 3 times 2 factorial over 2 factorial is 20 times 3 is 60, a much bigger number, right? So, and it's bigger by this factor of r factorial here, because that's the extra thing that we divided by. And 3 times 2 times 1 is 6. So this is 6 times bigger. And you can see that. So as these numbers get significantly larger here, especially for n, then we'll need to be able to calculate these bigger numbers, probably with a calculator. So, so the idea here is that with a combination, order does not matter. With a permutation, order does matter. We may have a worksheet coming up later specifically about combinations and permutations that may go over that entirely on its own, either from this textbook, or I may pull something else from online, just because it's such an important topic in statistics to know how to count things when order matters and when order does not matter. So typically permutations here have to do with when you do things without replacement. Combinations, and you can tell the difference between things. Combinations have to do with things where, like, I'm wanting to find the probability of picking a defective circuit board out of a batch when I know the total number of defective circuit boards. And let's say I'm going to pull going to pull 3 out, right? And of a group of 50, and I want to know the probability of getting exactly one defective. So there's something called the binomial theorem, which says if P is the probability of a success, and Q is that, we're going to talk a little bit more about this next time when we talk about probability of a failure. There are N trials. They're actually independent trials. Independent is a word that you don't know yet, though, that we might talk about next time. And then we want exactly X successes that we're going to have a formula that says that this probability, the probability of exactly X successes, is going to be N choose X, P to the X, Q to the N minus X, and this number N choose X right here is going to be able to be read right off of Pascal's triangle, or you have to use the formula method here, or you have to have a table to tell you that, or you have to use your calculator to do it. So this technique to use Pascal's triangle is really important for this probability theory, especially for what we call a binomial probability theory, a binomial PDF problem here, which is one of our types of probability distribution functions that we're going to deal with a lot in statistics, because we want things that are true or false, yes, no, good, bad, that we only have 2 options like that, heads, tails, and so on. So there we go. This is as much of an introduction to probability as I think that I can give you right now. And this is also extremely useful, like I said, in binomial expansion of a plus b to the n or a minus b to the n. And it's helpful in many other areas too. We just talked about one of the patterns that you can find in here. You see that there's ones, and then there's all the counting numbers, but these numbers here are called triangular numbers, and they're special. And then these numbers over here are something special, and you can see some patterns sometimes in this triangle that are really interesting if you want to learn more about Pascal's triangle and all the different patterns that you can find in it. Go ahead and search that on YouTube. There's plenty of videos that are out there. All right, I'll see you guys next time for some probability theory.